Good morning to you all.
Good morning, sir.
Yeah, morning. So we have 138, 139 students now. All right, I think we can start. Today, I'll be taking you Markov chains as part of the topics in FBA 410. Once again, hello?
Hello, sir.
Yes.
Hello, sir. We can hear you, sir.
Yeah, I was getting an echo, so I needed to change my device. So I guess it has stopped now. So sorry about that. So today we will be discussing Markov chains as part of the topics in FBA 410. So I shared some materials before now. So I hope you guys have received those materials. You already have your teaching schedule, so you should know who should be teaching you by this time. And then I sent this material. I also sent a recorded lecture for the previous set, and then I share the textbook with you. So I want to confirm that you all have those materials.
You only have the material, the notes.
Which one? You only have this slide, right? Please speak up.
Yes, sir.
If you don't have it,
Yes, sir.
share it.
Yes,
Okay,
sir.
so you
Yes,
only
sir.
have
We
this
have
slide.
the slide. We have the slide, sir.
We have
What of
the
the text?
slide.
We have not received that one yet.
Wow. I sent it about 2 weeks ago. Okay, so what you do now is somebody should just send me a hi now, and then I'll just forward it. So once I forward it, make sure everybody gets it. Do it now. It don't take. I'll just forward. So you just send me a hi, and then I'll forward the materials. It's disappointing because I sent it through the class governor of Actuarial Science Year 4. And I insist everybody gets it. Over 2 weeks. All right.
Sent it to us, sir.
Just hold on. I've seen
Sent it to us.
some of the eyes. So just hold on, please. No, you get it in the next 50 seconds. Did you receive any material?
Yes, sir.
All right. So I'll send another one now. I forwarded another text. So what is left is the recorded class. Please confirm that you have received the materials.
Yes, sir. Received it.
All right. So okay. So there's nothing stopping you guys now from maximizing whatever we teach you. So we are discussing Markov chains and what exactly are we looking at? I'll briefly describe and classify stochastic process. So what's a stochastic process? What are the different forms that we can have based on their state and the time of transition? So after that, I will discuss what the Markov property is, and then we will now snowball into the Markov chains, because the Markov chains will rely on our understanding of the stochastic process and also understanding of the Markov property. So after that, we will now discuss the properties of Markov chains, and then we take examples on the application of the Markov chain. So I have a case that I will want us to treat together. And that was why I was referring to the text material, which I thought you guys already have. So that will be the summary of what I'm expected to teach you, and what you are also expected to have learned at the end of the day. So I hope to achieve this within the next 1.5 hours. So what's the stochastic process? You guys are already exposed to different methods of analyzing data. During your FBA classes, you have been taught how to summarize the data in a frequency table. You have been taught how to build relationship between variables. You consider one variable as a predictor and the other one as the dependent variable. So basically, you know how to build regression analysis to explain relationship. But there are times that your observations are time dependent, such that the time at which that observation is taken has to be put into consideration for your analysis. And there are also times that you will have data that are based on classification. So how do you analyze it and you still want to make a projection? So that is where the stochastic process comes in. So our stochastic process is simply a collection of time-dependent random variables. Usually we use X to denote our random variable, and then the T, the subscript of it, will indicate the time at which that random variable was taken. So if you have a collection of random variables that are time dependent, you put them in a set, then what you have is a stochastic process. So we say that the stochastic process is a collection. Remember what you learned about set theory in your SS1. We're told that a set is a collection of well-defined objects, and then we use the brace to denote sets. So that's what we are using here. And that's why we use the brace, as you can see, as I've highlighted. So we say that the stochastic process is a collection, is a set of time-dependent random variable. This is the time-dependent random variable. You can see the subscript. The subscript has a T in it. The random variable is the X, right? So where your T belongs to the capital T. So the capital T there represents the time, all right? So it is like having a universal set and a subset. The subset is part of the universal set. So, and that is why you have the small t belonging to the capital T. But what we are simply saying is that if you are collecting observations that are time dependent together, what you have is a stochastic process. That process that brings them together, a stochastic process. So it could be your sales. So you have your daily sales, and the time at which you gather that data, if it matters to you, not that you model the data up and start analyzing, but the time matters, and you are tying the time to the observation, the sales that you have recorded. Then the collection of all those sales that you have is a stochastic process, right? So stochastic process is a collection of random variables that are time dependent. So, but there are some very important concepts that we need to understand about stochastic process. We have what we call the state space and the time set. State space and the time set. So the possible values that our random variable takes is called the state. So it could be the sales at day 1, the sales at day 2, sales at day 3. So those values, they are the state. So even if you are dealing with classification, we deal with classification, like the health status of an individual. The health status could be healthy, it could be critically ill, it could be maybe just sick. So, and then maybe we add the dead state to it. So that means there are 3 possible classifications that you can, place a human being at any given time. Those classifications represent the state. That's what we use. We use the term state to represent the value that you have at any given time. So it could be that at month 1, if you are studying the health status of that individual, and maybe 4 states is sufficient to describe the health status. At month 1, the individual could be in a healthy state. At month 2, the individual could remain in the healthy state. At month 3, the individual is now described as sick. Month 4, maybe the individual is now critically ill. Maybe at month 5, the individual transits to the state of death. So each of those classifications, they represent states. So the value that your random variable takes is called the state. Now, when you put all the possible states together, just as you have in your universal set, remember that our universal set is the set of all possible sets. So it is like a model set. So it's the same thing here. So the set of all possible states is called the state space. The state space. This is very important in classifying our stochastic process, because if you cannot classify your stochastic process well, then it will be difficult for you to know what method that you will use in analyzing the data once you have identified that that data is
Sir, we can't hear you, sir.
can be discrete.
Sir, we can't hear you.
Maybe does not know you're getting mute himself. Can't hear anything.
Hello?
Can hear you. Can hear you. Hello, sir.
So
Can
we
you
can't
hear
hear
you?
you.
Hello? So, so that
Can hear you.
means, oh, oh, sorry. When, what was the last thing that you heard before the,
The last thing was if we can categorize our space, then it will be
okay,
difficult for us to analyze our data.
Yeah, that was
all right, wow, all right. So let's go back to the time, the state space. So I was saying that the value that our stochastic process takes, or the classification that you place your stochastic process, is called a state. So it could be that if you are looking at the health status of an individual, and you have used a four-model um, um, classification to represent it. So the classification could be healthy, it could be critically ill, it could be sick or dead. So if you have those four classifications, each of those classifications is called a state. Okay, a state. So, and when you put all the possible states together in a set, just as you have in the universal set, then you have what we call the state space. Just like you having the universal, set, or you have your sample space. Your sample space is the set of all possible samples, that's a random variable. So it's the same thing. Yeah. So when you put all possible states together in a set, then we have the state space. So it could represent classification. It could also represent values. Okay, like you have in this example of the sales record. So your sales record, is tied to days. So on day one, your sales equals to 5. So if you are writing it, it will be X1 equals to 5. On day 2, the sales is 5 million, 200 million. So you now have X2 equals to 200 million, and so on. So when you put all possible sales together, so in a set, then you have your state space. Now, the time at which you take your observation. So the time could be discrete, it could also be continuous. So it is discrete if you can use natural numbers to represent them. That you have 1, that will be time 1, time 2, time 3. So the time could be day. So you can have day 1, day 2, day 3, and so on. The time could also be monthly, quarterly. So in that case, you have discretized the time. But however, the time will also be continuous, like you have in the if you are monitoring stock, for instance, or you monitor forex, and you have to do it in real time. You have to do it in real time. So that time don't have to be discretized, because it won't be 1 hour, 2 hours, because per nanoseconds you are taking your reading. So in that case, time have been they are in continuous state. So when you put all the possible time together, you have what we call the time set. Time set. So this concept needed to be well understood before you can classify our stochastic process well. Now let's look at how we can classify our stochastic process based on the time and based on the state. So to classify our stochastic process, there are 5 possible classifications that we can have. 5 possible classifications. So the state can be discrete, it can be continuous. The time can also be discrete, can be continuous. So when you combine the state and time together, there are 4 possibilities as you have in that contingency table. But however, there are times where our time could be mixed, such that initially you started counting and then suddenly you transit to continuous. So based on that, you can have 5 possible classifications of our stochastic process. So we have a stochastic process of discrete states with discrete time. Discrete state with discrete time. We also have a stochastic process of discrete state but with continuous time. Discrete state with continuous time. And then we have stochastic process of continuous state, discrete time. Continuous state, discrete time. And then you can have stochastic process of continuous state with continuous time. Continuous state with continuous time. And then we have mixed type processes. Mixed type processes. Now let's take them one after the other so that you understand them well. And let's look at the stochastic process of discrete time and discrete state. Discrete state simply means that the states can be discretized. That means you can be in one state at a given time. When you are doing the classification, it is not continuous. All right. And then the time at which you transit to the state have been discretized. Like you can have time 1, time 2, time 3, time 4. So when you have the combination of those two scenarios, then the stochastic process has discrete states and discrete time. So you can have an example of a classification of your customers as based on some level of discount, depending on the volume that customer is able to attain. You can classify the customers as enjoying 0% discount, 25% discount, 40% discount. And if you do your classification, your discount classification, you do it on a monthly basis, quarterly basis, or yearly basis. It means that the time at which you do the transition have been discretized. So in that case, if you are describing that process of classifying your customers into 3 different discount categories, then that stochastic process is of discrete time, discrete state. Remember, the value, the classification is the state, the time that you get there is your time. All right. So all possible time put together is the time set, and all possible states together is the state space. So this is an example of a stochastic process with discrete time and discrete states. All right. So let's look at the second scenario. Remember, there are 5 different classifications that you can have. So when you have a stochastic process of discrete time, a discrete state and continuous time. Discrete state and continuous time. So look at the example of the health, health classification of an individual. So a 3-state is considered here: the state of healthy, sick, and dead. I'm sure you all agree that the time of transition from any of those states is continuous. You can see someone that is very healthy in the morning, and then by 12 noon, they tell you that person is in the hospital, that is seriously sick. And then you see someone that is very healthy 2 minutes ago, and then they tell you that person is no more, that person has passed. So the time at which you transit from those states, you transit from one of those states to another, the time is continuous. All right. So there's no designated time that you will say that, okay, I will fall sick in 2 hours time. It's not possible for you to to determine that. It can happen anytime, okay? And it can happen in any nanoseconds. So that kind of a process is a stochastic process, although the state is discrete, but the time of transition is continuous. So there are several examples that you can also have. So if you can describe that process in this form, then you know that what you are dealing with is a stochastic process, but the time of transition is continuous. While the state, the state is definite at any given time. That state is discrete. So we also have the scenario where the state is continuous and the time is discrete. Let's look at the weatherman. Okay, we take weather and we are interested in the temperature. Temperature is measured. Temperature is not counted. So, and we know that readings that you get from measurement, they are continuous. Readings from your measurement, they are continuous. They are not discrete. So, so the states which represent the readings, they are continuous. So it's continuous state. But if the weatherman is giving you the information on a daily basis, say, okay, day one, the temperature is XYZ Fahrenheit or X. The time have been discretized. Time is discrete, but the state is now continuous. That's an example of continuous states, discrete time. And then we also have the scenario where the state is continuous, the time is also continuous. Take your crypto trading, for instance. The value of your coin is continuous because the value of your coin is a measurement. It has to be calculated using some metrics, and then you have it as 0.00000, maybe 0.0045, and then it could be 0.22222282. So those ones are not natural numbers; they are from real numbers, so they are measurements. And then even the time, the time that you take your readings to monitor your coin to determine whether you need to sell now or you need to buy now, that time is continuous. So in that case, you have your state as being continuous. The time is also continuous. And then finally, you have a stochastic process that is a combination of discrete time, continuous time, discrete state, continuous state. And those are the 5 possible stochastic processes that we have. Why is it important? Whenever you are analyzing data that is time-based, and that time is of essence, what you are dealing with is a stochastic process. And then, how do you treat it? So you need to understand how that data is taken. So you need to understand the state, you need to understand the time set, so that you can classify your stochastic process well. After the classification, then the tool that you will deploy for it will be dependent on the state and the state and the time. So that's why we are studying this, but we are narrowing down. We are narrowing down a particular one, so you can appreciate why we needed to understand our stochastic process well, and then we link it to our Markov chain. So if you don't understand how to classify the stochastic process, so how will you understand Markov chain? So, but before we do that, we need to introduce the concept of the Markov property. So, what is a Markov property? Forecast is needed for decision making. Most decision maker will need to have an understanding of their historical experience and then combine it with the current realities, and then they come up with a form of model that can explain all of those observations, and then they make projections into the future. So if you use that kind of model, so you are simply saying that your past experience matters in understanding how to treat the future. But there are cases where past experiences don't matter. So that it is only the current state that matters to you. So you don't keep memory of your past. So if you have that kind of scenario, that that is what Markov property is. That's Markov. That's what Markov property is. So Markov is saying that your next process depends, your next state depends on the current state only, irrespective of what has happened in the past. Okay, so let's take the example of the discount classification. You have your customers, and you are looking at the volume that they are able to make, and then you put them on discount level, right? So if they are able to make maybe 1 million benchmark, you put them on 50% discount. But if they're able to make 10 million benchmark, you put them on 50% discount. So one is enjoying 25%, one is enjoying 50% discount. So on what basis are you classifying them? On their current status. What volume have you made in the last 1 month? So even if that customer has been doing 100 million in the past, but currently is doing only 10, that customer cannot enjoy more than 25%. And whoever is making 100, maybe you put them on 50% discount. So that process is Markov, because you don't deal with the past, you deal with the current situation. So what matters is the current and not in the past. So if you have that kind of behavior, then we describe that behavior as Markovian, right? So if we describe a student as being Markovian in its behavior, then we are just saying that that student don't have memory, and that student the student only remembers what is being taught now, and not what he has been taught in the past. So the Markov property states that the next state that the process will be depends on the current state only, irrespective of the historical past. So it doesn't keep memory. So we need to take that into consideration. Remember, we are drawing down to Markov chains. So, but we need to understand what Markov is. So Markov is simply saying that, look, if I'm making projection, and what matters to me is what is happening now, not what has happened in the past. So if that is enough for you to describe the next, then we are saying that the process is Markovian in nature. So the Markov property states that the current state is what matters to predicting the next and not the past. So the time that a process stays in a particular state is called the sojourn time. And then when we say transition, the movement from one state to another, the term that we use in this particular topic is called transition time. The movement is transiting. You are transiting from one state to another. Avoid the use of the word moving from one state to another. So the right time to use is transiting from one state to another. And then the probability of the transition, it can also be termed as a transition rate. As the probability of being on one state at any given time, moving from one state to another. It's called the probability of transition. and then that probability can also be used, can also be termed as transition rate. And most times, when you're dealing with classification, moving from one state to another, you can use a matrix to represent it. I'll show us a typical example, which I will derive using my Excel. So, now, what is Markov chain? What is Markov chain? So I'm sure you are seeing the interesting expression we have on the screen. So we will simply say that a Markov chain is a stochastic process that has the Markov property and whose state is discrete. I'll take it again. Forget about what you are seeing on the screen. If you can write it the way I've explained it. You have got it. But the Markov chain is a stochastic process that has the Markov property and whose state is discrete. Now, look at what the expression is saying. It's saying that the probability that a process at time n plus 1 will be in state J, given that at time x naught, that's at the beginning, is on state k naught, and at time n minus 1 is in state k n minus 1, and at time n is in state I. If it's the same as probability that the process at time n plus 1 will be in state J, given that at time n is in state I, that means we're not bothered about the time 0, we're not bothered about time n minus 1, and what concerns you is just time n, and time n is the one preceding time n plus 1. So that's what it's saying, that look, if you have your process that you can describe as this, then it's Markovian, provided that these states, okay, the time of transition, look at the time of transition. The time of transition is discrete. So if you have that, then what you have is the Markov chain. All right. So look at it, that a process with a finite number of states in which the probability of being in a particular state at step n plus 1 depends only on the state that is occupied at step n. All right. So if you have that, this is what you state, you are still correct. But it's easier when we use that mathematical expression to make life easier for us and to make it more concise. So whichever one that you feel is convenient for you, you should use. So we have our Markov chain now. So you should understand what your Markov chain is. Your Markov chain has to be a stochastic process that possesses the Markov property. That's the first condition. Markov property must be obeyed. And what does the Markov property say? The current state depends on the next state depends on the current state only, irrespective of the previous states. That what makes it to be Markov property. Then what makes it to be Markov chain? It is the state. Okay, the state has to be discrete. All right, so it has to be in the definite state at any given time. So the states have to be discrete. That's when it is Markov chain, and the time of reaching it must be discrete. Markov chain. But if the time of reaching this state is continuous, then what you have with the Markov chunk. But that is not our focus. So our focus is now Markov chain. So you can see that we needed the knowledge of stochastic process, and we also need the knowledge of Markov property for us to define and understand the concept of Markov chain. Okay, so a Markov chain is a stochastic process that has a Markov property, and the state is discrete, and the time is also discrete. So that's our Markov chain. So let me share an Excel sheet with you. Let's look at a typical classification and how we can derive the transition probability. Hello, are you guys still with me? I hope everybody is.
Yes, sir.
hearing-
Yes, sir. We are with you, sir.
Yes, sir.
Yes, sir.
Okay, so
Yes,
let's
sir.
assume that we have 4 different classification that you can place your customers. So you have discount level. Okay, let's make it 3. Discount level A, discount level B, discount level C, and then put them A, B, C, A, B, C, B, A, C, B, C, A. All right, so let me make it shorter so that everything will be on the screen and then we can easily understand. So these are the classification over time. So, and you want to represent this in a concise form. You want to summarize that. So, all right. So this means that so we have a way of classifying. This is the current state. Current, so this is the current. Okay, and then I am putting them here as the next. Okay. So next state. All right. So not that. Not that. So the state can be 1, 2, 3, ABC. Okay. ABC. And then the next state could also be A, B, C. Since you have your customers, so what we're saying here is that the customer can be classified as A, B, or C now, and then in the next period or 2, there will also be classification into 3 different possibilities. Now, how do you summarize this in a table? How do you summarize this in a table? So what you need to do is look at how many times you have A following A. Because here means that what you have here simply means currently you are in A, and then you are moving to A. Is that what it means? So you now look at your record and check how many times do you have A following A, and that is what you keep in here as your observations. So after we are done, we will now add up each of the rows and then use the total to divide the element, and that gives you the probability that if you are currently in A, the probability that you will end up in A after the next classification. So let's count. So here we have A following A, that's 1. We have it here 2. A following A, 2. And then you have another A following A, that's 3. That means it's 3 times that you have A followed by A. Now, AB simply means that you are currently in A, you end up in B. So you are looking at the number of times that you have B following A, B following A. So in that case, look at this. This is 1 because there's an A at the beginning and then B follows it. That's 1. This is another 1, 2. Here, B. So there are 3 times where you have a B following A, 3. And then C. How many times do you have C following A? I mean, you look at the pairs of AC, 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 AC. That's what you're looking for. So there's no AC here. AC, AC. There's 1 here. Can you see it?
Yes.
There's 1 here. So just once that you have experienced it, and then you keep it 1. And then BA. BA means that you have B, and then you have A following it. So BA. That's what you're looking for. BA. So you have it here. It's just 1. BA. There's only 1. So you have BA 1. And then BB simply means you have B following B. There's no such case here, so this is 0. And then BC means you have B, C1, BC2, BC3. Is there another one? No. So you have 3. Okay. 3. Sorry. 3.
There's another one, sir.
Another one.
Another one, sir.
Yeah, another one.
It's 4, sir. Yes,
4.
sir. At OP.
Yeah, let's do it together. 1, 1,
2, 3.
2, 2,
3.
3,
And then, yeah, 4.
4. Yes, thanks. Okay, so now let's move to CA. This is 1, 2,
2, 3.
3. So we have 3. Then CB.
1,
1,
2.
1.
Mm,
We have to.
2, sir. Yes, sir. It's 2.
Okay, 2. Yes. 1, 2. CB is 2.
no,
Now let's look at 6. 1. It seems we have 1, right?
Yes, sir.
Okay, so 1. Now let's add.
one.
So the total will be
Yeah, just one, sir. Yes.
the first one is 7.
7,
Second one is 5.
5,
6.
6.
So now we can get transition probabilities. Okay, transition probability.
Yeah,
Elizabeth,
Yes, sir, I don't really understand this stuff that we just did. I understand how we were doing the current thing, but I don't understand the purpose of how exactly it is with the Markov chain. I don't know the relation. I really do not get
yes.
it.
So I want to show us how the transition probability is obtained from first principle. Then I also want to show us how the transition matrix is obtained from first principle. Look at the data that you have. Look at the raw data. You just have classification. But look at what we end up getting. We already have our matrix. This is a matrix. This is a matrix. So you have been able to interpret the raw observation in the matrix form. So what is next? What we have got is the summary. Now we want to get the transition probabilities. What is the probability that if you are currently in state A, that you will end up in state A at the next classification? That's what we want to derive now. So I can only do that by dividing each of the rows by their row total. Each of the rows by their row total. So let's quickly get that. The transition probability. So you have each of these now. That will be this divided by 7. Now you are dividing each of them by 7. So, and what you have is this. So let me make it to. If I make it to 1 decimal place, it might not add up to 1 based on what I observe. So this will be equal to that divided by 5. Where did I get the 5 from? The 5 is the total for the row. So, and then the last one is divided by 6. And then, so if you check, you will see that each of the rows add up to 1. So what I have here is the transition matrix. The transition matrix. This is how the transition matrix is obtained. So this is a stochastic. This is the Markov chain. You will see that the next state depends on the current state only, 1. So that's Markov property. Then the time of transition is discretized. So you can see that at any given time, you have A, B, C, and then the states that you transit to, they are also discrete. So this one makes it a Markov chain. All right? And then what you have here is the Markov, is the transition matrix. So we'll still come back to it. So let's go back to our slide. So now, our transition matrix have a property. Number 1, each of the matrices is non-negative, so there's no negative probability. And then number 2, the addition of each row is equal to 1. The addition of each row is equal to 1. Now, what do we have on the screen? What do we have on the screen? This simply means, look at it, it simply means probability that a process at time n+1. The subscript is the time. When you say equal to, what you have after the equal to is the state. X, remember, is the process. So you say that the probability that the process at time n+1 is in state J, given that at time n is in state I. All right, so that's how to interpret it. The time is the subscript, The process is the X. The state is what you have after the equal to. So it has the property that the addition of the rows must be 1 and that each cell must be non-negative. All right. So when we draw the graph of the transition matrix, we have what we call the transition graph. This graph, as we have on the screen, actually represents the transition graph. Now let's see how the graph was drawn. So there are 3 circles. Each of the circles represents the states. Now look at what we have on the screen. There are 3 states. Okay, 3 states. 1, 2, 3, and that's what represents each of the circles. Now you will see that the probability that the process starts from 1 and ends in 1 is 4.65. That's why you see the arrow. Look at the arrow moving from 1 and then coming back to 1, 4.65. Now, the next is probability that the process is in 1 and then transit to 2, 4.28. Now look at it. This is 1. Transit. Look at the arrow moving from 1 to 2, 4.28. The third one, the probability that your process is moving from 1 to 3. From 1 to 3 is 0.07. That means the arrow will move from 1 and then go to 3. Look at it. You see the arrow, you see the direction. 1 to 3, 0.07 at 0.07 here. Then you also have the transition from 2 to 1. 2 to, I mean, the arrow will move from 2 back to 1. From 2 back to 1. That's 0.17. The same thing, probability of being in 2 and then remaining in 2. So the arrow will start from 2 and then goes back to 2, 0.67. And then from 2 to 3, so means the arrow will move from 2 and end up in 3, 0.18. Then 3 to 1, the arrow moving from 3 to 1. So that means you will have it from 3 and then going back to 1. That's 0.12. Look at it, 0.12. And then 3 to 2, that means the arrow will move from 3 back to 2, 0.36. And then finally, the arrow starts from 3, end up in 3, 0.52. That's how it is obtained. Okay, that's how it is drawn. So if you are asked to draw it, don't say you can't draw it. It's straightforward enough. And then use the arrow to denote the direction of movement. Okay, so let's look at this case, and then we'll look at how do we now deal with the probabilities. How do we deal with those probabilities that we have obtained? Now I want you to have a look at this question, this example. I'll give you 30 seconds to have a look at it, and then 30 seconds. Look at it. All right, so let's look at that example. So you have a meteorologist studying the weather in a region, decided to classify each day as simply sunny or cloudy. After analyzing several years of weather record, he finds that the day after a sunny day is sunny 80% of the time and cloudy 20% of the time. And a day after a cloudy day is sunny 60% of the time, and it is cloudy 40% of the time. So which means that these states have been discretized. There are just 2 states, sunny and cloudy. And then the time of the transition, it has been discretized too. Look at it. It's now daily. Now, so the weather. Hello? Someone is asking a question? All right. So the time is discrete. The state is discrete. And then if you look at the scenario being described, we're looking at the day after. Okay, the day after the particular classification. So that means you don't look at previous or historical records. It's just one day apart, that you are taking your measurement. Just
I have a
similar to
question.
the example of, yes. Go ahead.
That is, time is discrete, and this is 80% of the time. That's 0.8. Well, I don't get why it is discrete, sir.
No, 80% of the time it's a probability statement now. That 80% is the probability that a sunny day will follow a sunny day. That's the interpretation. The probability that a sunny day will follow a sunny day is 0.8. That's the meaning. Because it says that the day after a sunny day is sunny is 80% of the time. That means when you look for SS, as we had in the case of our A, B, C, D, looking at when do you have SS as pairs. So it's 2.28. That's the meaning. It has nothing to do with the state. It has nothing to do with the time of transition. Because the time is there. It's saying each day. Look at it. It's saying that the region decided to classify, look at it, to classify each day. That means the time of the classification is each day. And then what is the classification? Sunny or cloudy. That's where the time has been determined. Even the state has been determined. The rest is just the probability as they have got over time. So yes, you are free to ask. You are free to ask because you need to understand it.
I understand, sir. Thank you, sir.
All right. So now let's look at the transition probability as obtained. What you're supposed to have here will be A or S, sunny. And then you have your C here, cloudy. And then you have S, sunny here, and then C here, cloudy. So S to S, 0.08. That's what the question says. And then S to C is 0.2. And then C to S, cloudy to sunny, 0.6. Then C to C is 0.4. So it's so straightforward that one can easily put this. And then look at the transition graph. The transition graph too is also straight. Your S remaining S, that's where the arrow is transiting back to S, 2.8. Look at the C, remaining C, the arrow transiting back to C, 2.4. And then you see, moving from S to C is 0.2. Moving from C to S is 0.6. So that's an example of it. And then you have different cases of Markov chains. You have the regular Markov chain. You have the absorbing Markov chain, and so on. So a state is said to be absorbing if transition from it is impossible. Okay, like you have the state of death. Once everybody transits to a state of death, that's all. You can't move out of it. So that is a typical example of absorbing state. So if the probability of transiting from that state to any other state, if it is 0, then what you have is the absorbing state, right? So now let's look at how we can deal with our probabilities. How do you use it? How do you use it? How do you use that transition probability? So we use the n-step probability. to make our projection that okay, this is the current state. Now let me go back to my Excel, do some multiplications in Excel, and then come back so that you understand what this state, what this slide is talking about. Now I'm currently in my Excel. I have let me copy out my transition matrix. All right. So I have my transition matrix, and let's call this capital P. Okay, my transition matrix. Now, if I multiply P by itself, remember it will give me P squared. Going by our knowledge of algebra, P times P will give me P squared. Now, P to power of 1 simply means the probability of transiting from one state to another at one step. That means maybe after 1 year. Now, if I have P to power of 2, it simply means probability of transiting from one step to another or from one state to another after 2 years. That's why it is P to power of 2. So if I want to get the probability of a process that is currently in state A, the probability that it will end up in state C after 3 years, what I need to compute is P to power of 3. So generally, P to power of n will be the transition probability after n step. Each step is one time. It's one time, this one discrete time at a time. So that means if I have 2 steps, so it will simply be P to power of 2. It could be 2 years, depending on how that time has been defined. So if I have 3 steps, then I need to compute P to power of 3. If I have 4 steps, I need to compute P to power of 4. So if my step here is defined as years, then it will be after 4 years. What will be the probability? All I needed to do is to compute P to power of 4, and then I will get that probability done. So you guys have done matrices before, and you know how to do matrix multiplication. So my job is not to teach you matrix multiplication, but I'll just show you how you can do it, so that when you go home and start multiplying, you can use that to cross-check whether you are right or wrong. So P to power of 2 here, you simply mean using P to multiply itself. So I'm supposed to get a 2 by 2 matrix as well. So let me use that matrix to multiply itself. So the content will of course change. So how do I multiply? I'll create the cells where I want the multiplication to be, and then I'll type equal to. All right. So the function to multiply is mmod. Mmod simply means matrix multiplication. And then you now select the first matrix, which is this one. All right. You put a comma, and then the second matrix. Because I'm using the matrix to multiply itself, so second matrix will also be the same. That's all. So you can press Control Shift equal to, and then I have that. All right. So this is the matrix. If I use this to multiply itself, it simply means, now look at the first year, the probability of transiting from B to B. Remember, it was impossible in the first year. But look at the second year, from B to B, it's 0.35. So that means there's a 35% chance that a customer that is currently enjoying discount level B will keep enjoying discount level B after 2 years. Look at it. But after 1 year, it's almost impossible because the probability is 0. But after 2 years, you have 35%. So and so on. So let's do B3. I'll just stop there and then go back to our slide. B3, P3, P to power of 3. So again, I'll copy so that I'll delete this. So again, I will highlight where I want the result to be. I type equal to M mod. M mod means metric multiplication. So by the time you type double M, the M mod will appear. Just double click, and then our P3 will be P times P squared. Remember your algebra. So I'll select the first matrix command, and then the second matrix P3, and then I'll press Ctrl Shift Enter, and then I have that. So it's very simple. So now you can compute depending on how many steps that you want to take. So each step simply means raising the probability to that power of step. Okay, so one step is P to power 1, 2 steps P to power of 2, 3 steps P to power of 3, and that is how the projection. That's how the projection is done. So let's go back to our slide. Please, you are free to ask me questions, please. You don't just have to keep quiet even when you don't understand it. All right. So now that's what this slide is just simply explaining. Okay, it's just simply explaining your matrix algebra. How do you raise your matrices to power of 2, to power of 3, and so on. So it has nothing to do with what we have been working on. It has nothing to do with a Markov chain, or it's just your matrix algebra, things that you're supposed to know at least before now. So again, this is our probability. All right. Now look at 2. 2 is an adsorbing state. Can you see?
Hello, sir. Hello, sir.
Yes. Yes.
Hello,
go
sir.
ahead. Yes.
Sorry, sir. Sorry, sir. Please, I don't understand the multiplication P2 because matrix. Sir, what if we are doing it manually? So how is it going to be, sir?
Exactly.
What if
You can do it manually, and you use the manual method. The normal way that you have learned how you have learned. Normal ways, how to multiply matrix. You will use the rows. You use the rows to multiply the column. For example, now, if I'm multiplying P and P, so I will pick this row, okay, 0.43, 0.43, and 0.14. I'll use it to multiply this column to get the first element. So I pair them, I multiply, and then I add. Then again, I pick the first row again to multiply the second column. After multiplying, I add up. Then lastly, I pick the first row to multiply the third column. And that will give me the third cell for the first row. Then I repeat the same thing for row 2 and row 3. You have learned it before, so you know it.
Hey, Jesus Christ.
So don't worry, just review things that you know, and then you'll be okay. Don't worry, you'll be okay.
Sir. Okay, sir.
Sorry, sir. Sir, will you share this Excel with us?
Yeah, if you want me to share it, of course, I'll share it.
And the class record, sir. The class
Okay,
record
sir,
is very
please share
important,
it.
sir. Thank you, sir.
It's still there, but
all right. So this is just explaining the absorbing state. Now look at 2. The probability of transiting from 2 to 2 is 1. That means you're not moving anywhere. You go back to 1. If it is 1, then you have state 2 is an absorbing state, because once you move in there, you can't move out. All right. So and then the properties of a Markov chain, it has to be irreducible. Irreducible simply means that you should be able to reach all states from every state. That means from 1, you should be able to reach 1, 2, and 3. From 2, you should be able to reach 1, 2, and 3. From 3, you should be able to reach 1, 2, and 3. It's desirable. If that is possible, then you say that that Markov chain is irreducible. Okay, and it has to be ergodic too. Okay, it has to be ergodic, so which means that the time is finite. All right, and then finally, it should have stationarity behavior. Stationarity behavior simply means that at certain time, if you keep multiplying the matrix by itself, you get to a state where if you multiply P by P to power of n, the value remains the same. Okay, from that point onward. So that means it has reached a stationarity level, or you have attained the limiting state or the limiting distribution. So it is desirable for a Markov chain to have that, because it means that the Markov chain behavior is tractable, okay, over time. So this is, and then we have examples where the Markov chain, it's applied. But I want to take a typical example from the textbook, and I have my reasons for using that. I was told that, and I'm sure you also know that all exams have to be pen to paper. Are you aware?
Yes, sir.
Yes, sir.
No, sir.
So okay,
Yes,
okay.
sir.
Now
But
that
is
now
FBA
you are
going to
aware,
be
No,
OBJ?
sir.
the guy that said no. Now you are aware that your exam
Sir.
will be pen to paper. All right.
Sir,
So
Hello, sir.
sir,
yes, I'm listening.
we
Yes, sir.
we receive lecture online. Yet they expect us to come and do pen on paper.
Okay.
No problem.
Sir, help
But
us,
but you have been
help
but
us
you have
talk
been
with the management, sir.
all right.
Sir,
But you have been informed that the exam will be pen to paper. So that's why I don't want anybody to fail Markov chain. All right. So that's why I want you to have a look at what I'm going to do next, and I want you to pay attention to it.
okay, sir.
Now look at this question. I want you to pay attention to it. Pay attention. Okay. I've mentioned pay attention now about how many times?
I think there's
About 7 times.
Several times. All right. So now let's look at this particular example. I might not give you a 3x3 matrix so that you guys will not find it difficult to multiply.
Don't give us 3 by 2.
A 2x2 matrix will be very nice for you to quickly work on in the exam, and then everybody will be okay. Now look at this example, LO3, number 12. It says the company is using Markov theory to analyze brand switching between 3 different brands of DVDs. So data has been obtained and used to estimate the following transition matrix, just the way I obtained the transition matrix. So the current market share, so that means there are 3 different brands, brand X, Y, and Z. But the current market share for X, Y, and Z are 45, 25, and 30 respectively. Okay. So number 1, we need to obtain the expected market share after 2 months. And then what market share and the 3 brands expect in the long run. And what will you expect the actual market share to approach and the expected long run, prediction for the market. So what this question is saying is that you already have the propensity to switch, because the transition matrix is the propensity to also switch, the probability of them switching from one branch to another. So after 2 months simply means that you should multiply the matrix by itself, so you get p squared, and then you will use the 45, 25, and 30 to multiply the p squared, and that gives you the expected market share after 2 months. Let me solve it. So I want someone to open his own slide. Sorry, your textbook to page 848, so that you'll be reading out the probability to. So I don't. It won't be convenient for me to be switching from Excel back to this because it's not copyable. So the current market share is 45, 25, and 30. Okay. So let's go back. Let me current market share. Remember, it's X. Oh, I don't want to mix the two. So when you are reading it, you understand. Okay, current market share. I have X, Y, and Z. So the current market share is 45. Is it 45? 45%.
Yes, sir.
45, 25, and 30.
4.25 and
4.3.
That's the market share. And then your P, the transition probability given. Your P. So X, Y, and Z. Yeah, someone should read out the figures. For X, the row.
For X, 0.8,
0.8, 2.1, 2.1.
0.4,
0.8, 4.1,
0.1.
4.1. Okay. So the next
0.3,
4.95, 0.03,
0.95,
0.95.
All right. So let me expand the cell so that I can show. All right. Then Z, 0.2, 0.05, 0.75. 0.2, 0.95, right? 0.05, right?
Yes.
0.75. All right. Okay. So the question says after 2 years. So I need P squared. P to the power of 2. Right. So let me copy the whole of that, and then now I'll just so let me delete this. So I press equal to. So I'll use the P to multiply itself. So M mod, that's basically multiplication. I take that, and then the first is P, comma. The next is also P. I use P to multiply itself. And then I press Ctrl Shift Enter. So that's the probability after 2 years. That is how the switching behavior will be after 2 years based on the transition matrix that we have. But now you want the market share after 2 years. Market share after 2 years. Now look at it. Market share after 2 years. Let me just type it. Market share after 2 years. So what you need to do is to multiply. You multiply the current market share with the P squared, because you want to compute the market share after 2 years. So it will be the current times the P squared, all right? So again, I will just do my, where I want the result to be. The result won't be more than 3 cells, because it's just X, Y, and Z. Okay, to make life easy, let me just put them there. X, Y, Z. Okay, so the market share will now be M mod equal to, so I'll highlight the 3, equal to M mod. Once you put that double M. So the current matrix is the current market share. This is the current market share. So I put it there, comma, and then P squared. You now put P squared as the second vector. That's all. So you now press Ctrl Shift Enter, and that's it. That's the current share. That means after 2 years, X will take 41% market share. Y will be 33.9% market share, and then Z will be 25.5% market share. So who is losing? Now let's have a look at it. Who is losing? You can see that X has dropped. Y is the big gainer. Z is also.
Sir, please, can you calculate the market share after 2 years?
Applied. Now let's go back to our slides. Let me save this so that I can share it.
Can I have a question?
Please go ahead.
Okay, if we have to calculate manually, after getting our matrix, the P square, so in order to share the to calculate with the shares, like the given market shares. So
Go ahead.
matrix. Sir. Okay.
I didn't get the question. It was tracking.
Okay. The question is, after getting our matrix, like the P square, after getting the matrix, the market share was given to us for each for like each X and Y Z. I like we got to like use it like by color, because you don't do it like, because we have to do it manually. You know, we are using Excel to do it.
No. If you are doing it manually, you will still get the same result. I was only trying to be just smart about it. Otherwise, we will end up wasting so much time. And then matrix multiplication is not what I should be teaching you. At this level. Whenever you are in 400 level.
Yeah, I know, but
What I will do is okay. In what the textbook that I've shared with you, in their example, you will see that they showed how the matrix multiplication are done.
Okay, sir.
So that was why I shared it. And then the other one, the one for Taha, is actually, there all the steps that you will use for multiplying in matrices in Excel is there. The whole process is there. in Excel. So you can follow it. Even for all other topics that you did in your QA. They are there. So, ladies and gentlemen, this is what you need to learn under the Markov chain and how it is applied. And you can read more, watch videos, and so on. And you shouldn't go beyond Markov chain. Please don't go to Markov.
Sir, excuse me,
Sir,
sir.
we can't hear you.
Good morning, sir.
Yeah, morning.
Oh, we can hear you, sir.
You can't hear me?
We couldn't
Yes,
hear
sir.
what you were saying earlier, sir.
Oh, so I was wishing you the best, and I said that you can watch more videos. You can
Sir, the
solve
third question
questions.
in that example has not been answered.
What is the thought? Okay, the limiting. So the limiting, I was only saying that the limiting is not required for you for what I will examine. So that's
Okay.
that's the interpretation of
Please don't forget.
you have to learn how to read body language. So I'll see you guys in the exam hall. So I
Excuse
wish
me,
you all the
sir.
best.
Please,
Sorry,
check
sir.
Like
Good
that.
morning, sir.
Please, I have
Check
a
the
question. The
Excel.
recording, sir. The video
Sir, the
recording and the
Excel.
slide, sir.
Good
Sir,
morning,
you
sir.
said
Please,
I'm
we
the
have
video
the
recording, sir.
Oh my God.
Allah.
Good morning, sir.
Sir, can we get
Allow
you?
sir. Video recording, sir. Sir, you said we
Good
shouldn't go
morning, sir.